Okay, awesome. Okay, so back to our lectures here. I'd now like to talk about ABM, or more broadly, this is ABM conceptualization, but it's really conceptualization of models in general. So, ladies and gentlemen, the dynamic modeling process is a multi-stage one. It's one that involves iteration, but it also has associated with it a set of fairly well-defined stages. The first stage is the one we're going to be talking about for the balance of today's lecture. And that has to do with model conceptualization over here on the left-hand side. Setting the boundary of the model, deciding what things are to be left out of the model, what things are to be pre-specified to the model, and what things are going to be generated by the model. Things that are ignored, things that are exogenous, things that are endogenous, respectively. I'll introduce those terms again. And arguably, this is the most important of phases. If we choose a model conceptualization that's too ungainly or that's too impoverished, we'll have little chance of accomplishing often our goals with the model. So it's very important. After this phase, we'll be talking about a problem mapping phase, which will be a little bit different for each type of modeling, okay? Where we sort of map out a model in terms of how it might be composed, okay? And then we'll go and we'll formulate a model mathematically, where we actually have precise characterization of how the elements of the model interact. Following that, we'll often engage in a process of sort of confidence building about a model to sort of understand the degree to which it matches empirical data, matches data from the world. Develop confidence that it's actually meaningful and sort of characterizing aspects of the world. And we'll engage in a set of processes for testing it along with that, which draw to a certain degree on testing processes for software, for software development. Following that, we'll often use the model and use it to communicate to others. But our goal today is really to focus on problem conceptualization for the balance of the session. Okay. Now, agent-based models, and indeed the other types of modeling, but it's particularly true with agent-based models, support very, very rich characterization of behavior. And it's very easy to add extra levels of detail into a model. And for all these reasons, because any of these modeling types, in fact, can be used to characterize things at a more extensive level or a more parsimonious level, there's a need to be cautious and clear-headed about model scope and to proceed in a step-by-step fashion. Now, there's a principle that's articulated in software development, and some of you indeed will have heard me in 205A over in Thorvaldsen expound on the Agony Principle in software development. This principle says ya ain't gonna need it. And the idea is that in software development, we as software developers are often tempted to speculate about all the components that we've required in our software over time. And often, when we actually start building it, the stakeholder takes a different turn, and that feature, which we thought would be so useful, ends up not to be requested or not prioritized. So sometimes we have a tendency towards over-engineering our software. And so it is with models. There's a tendency to try to build all sorts of things into them. And often that takes time away from other things that are more important. And perhaps even more important, it limits our learning because the model becomes so complex it's hard to learn from. So I mentioned several components that we'll be talking about, but a key point is this notion of opportunity cost. putting something in often means not putting something else in. And often we are in a much better position to decide what to put in after some experience with the model rather than doing it up front. And hence an emphasis on incremental model development. I would note a direct parallel to software development. In software development, we talk about agile software development processes. Well, pursuing software development in an iterative, incremental fashion, where we experiment with putting in a new feature, we secure stakeholder feedback from a client as to what they think, and they tell us if we're on mark, and they'll often clue us into and talk with us about next priorities for the development. We're learning there how long things take to develop, and if we're running short of time, we may axe features we originally anticipated might go in there, or the stakeholder will point us in a new direction we didn't anticipate. So once again, both processes, modeling and software development, involve learning over time, learning from a stakeholder, learning from the model and stakeholders in modeling, and choosing a different route forward accordingly. Choosing a route that's more informed, that's more savvy. Having one. So incremental model development, as in software, is in my view key for contained modeling projects. So the idea here is, and I'd like to mark my words, particularly those of you pursuing projects, this is key. You would ignore this at your peril, okay? And this is certainly can feature highly in an exam. So the idea is to build in a step-by-step fashion. Now with each iteration of the model, each version of the model is modified in some small coherent fashion. You add in some effect or some new factor in the model and its effects on things. And then you experiment with the model. Before you do that experimentation, often you do what's called docking it against older versions of the model. In other words, you test, okay, how does this new version behave compared to the old one? And particularly, you may temporarily disable these new features and just make sure it still gives comparable behavior. And then you enable them and you see what their effects are, okay? So in short, you build confidence the model hasn't broken the old features, and that the new features, you have an understanding of what behavior they lead to, okay? And often these incremental versions can be demonstrated to system stakeholders, okay? Now, why do we undertake this? Oh, why do we undertake it in software development? There's a certain amount of analogy, but then there are some things about modeling that make it even more important. One thing is we learn with greater clarity from the model. There's a lot of things that come out of these models, you'll see. That very first model we looked at was notable for its extreme simplicity, but even there we could get some kind of interesting behavior that emerged from it. Behavior we couldn't anticipate, at least the details of it. And often when we're dealing with a model that's more articulated, that has more things in it, we need to understand where certain patterns come from in that model. So if we build it in a step-by-step way, small steps at a time, adding one thing at a time and experimenting, we understand where certain patterns come in. We'll see a pattern of a waveform that comes in at a certain point. We'll see a situation where it exhibits a tipping point. Above a certain thing, it goes this way, otherwise it goes that way. And we see where that comes in the whole process. We'll see things where it cycles in some way, and we see where that comes in. We see big disparities between different areas of the space, and we see where that comes in. So in short, we have an understanding where these patterns come up. Also, developing incrementally, like continuous integration in software, allows us to more quickly diagnose bugs and zero in on the cause of those bugs. In continuous integration, I see some familiar faces from 371, who I welcome. In 371, you may remember one of the big motivators for continuous integration is, look, if we bring people's contributions together, we do a continuous integration build, and there's some problem that results, it's quicker to track down where that came from because fewer things have changed. If we were checking things in once a month for everyone's contributions and something goes wrong, we have to go through a heck of a lot of changes in the code to figure out where did this go wrong. You know, the bug can live in all sorts of places. If we're doing a build and a smoke test, every check-in by each developer, and something goes wrong in one of those, well, often a small number of lines of code have been changed by that particular developer for that check-in. And we can be able to go in and find what went wrong more quickly. We can narrow it down up front much more quickly than if we were to put it all together once every few months or once a month. That may sound odd to you, but believe me, when I was a young man, when I was your folks' ages, often you would have software that would come together once every few months. You would have all these people working on it for a couple months and you put it together. It was called the Big Bang. Big Bang because it would lead to badness. It was like an overflowing amount of badness that could come from it. Like things didn't break, things didn't compile, things didn't work, things broke, things didn't compile. Lots of badness would happen every few months. And these days we're in a great situation because the badness happens in small bits every day, and it's much smaller bits because we have much less to worry about where it came in. We can quickly track it down. A key thing, though, ladies and gentlemen, with modeling that comes out even more so than in software development, much more so, is, ladies and gentlemen, these models produce surprising behavior. Often they surprise us. And when we are surprised, we can learn from it. And often that leads us to change our direction with the model, what we're going to put in next. We decide to experiment more with something because it leads to such interesting behavior. We decide, oh my gosh, of course I didn't realize that's a logical consequence. So in order to deal with that, I need to put something else in instead. In short, it changes our sense of what's the next priority. Why? Because we've learned from working with the model. By running the model, we observe something we didn't expect, and we end up needing to change direction based on that, to put something in. Okay, you could take that model, like with continuous integration, like with agile development processes, you can take a model and get feedback from stakeholders. You're not in the situation, well, we won't have the model ready for you for another 3 months. You're like, well, okay, tomorrow I could show it to you. Get some feedback. One of the strange things about modeling, ladies and gentlemen, is similar to a strange thing about software development. Mark my words, if you never do modeling again in your life, after this class, so before the end of the class, in software development and in modeling, you have this curious phenomenon that you wouldn't expect. Stakeholders, people who are interested in your model or your software, often they can't give really fulsome feedback about what they want until they see it. Until they see something in front of them, they have trouble imagining what it will look like, what it will do, how it will behave. And it's a matter of hubris on our part as computer scientists often, that we think, well, we should be able to go ask them what they want with their software up front. We should be able to go ask them what needs to be in the model up front, and then just do it. And that is simply not true. Often, their greatest insights about what they want, what they're seeking, what's relevant, what data they know of relevance to building the model. Their understanding of the system doesn't come out until you show something to them. You show them something. Now, it could be a very straw man thing. It could be far from what they want, but it will get them thinking in concrete terms about what they really want. Now, I wish it weren't so. I wish we could go and we could elicit their requirements in sort of an upfront way and go build them and give them just the thing they want. But often that's not the case because they don't really know until they see it. Other things interfere as well. Their sense of what's important to them may change in the meantime because their business has changed, or their needs have changed, or their thinking has changed. In any case, the point is that by iterating with feedback from stakeholders, taking this thing to them and showing them a model, you often get a lot more understanding from them about what's wanted or what the relevant data is, or get them to challenge things, or get them to support what the model is saying it's right on track, or what have you. And this is really important. It gives you greater clarity and prioritization. You can figure out when you're going to get to the next milestone of the model more clearly if you're doing it in a step-by-step way. You can say simply, okay, we've been doing it for a week, we'll stop now, give this to the stakeholder. It enhances stakeholder confidence. They actually see it coming along. Those of you in 371, you had those five incremental deliverables, right? You brought it to stakeholder. The fact that they saw it coming along gave considerable encouragement to their sense of buy-in. With models, it's very important that most stakeholders not see it as a black box, but see it as something they have some interest in. They see what it's doing. They develop not only a sense of confidence, but a sense of what it's doing and how it works over time. And it gives confidence you're making progress, and you're making progress in a meaningful way. And hence it can improve morale on the part of developers and indeed on the part of stakeholders. Okay? So when selecting the model boundary, selecting the model sort of scope, so what's in there, we need to characterize, we need to think about questions on an ongoing basis, on an incremental basis. Typically, we are thinking about, okay, what needs to go next into the model? What is the next priority for building in? And some of that comes from stakeholders, but some of it comes from a set of other considerations. Considerations involving whether we need to capture certain interventions, certain changes we want to make to the system. We want to ask certain what-if questions. What if we cut back on the number of otters harvested per year? What if we put a moratorium on hunting of the stellar sea cow? What if we expanded the number of spots in the transitional care unit of the Saskatoon Health Region? How would that affect things? So if we're interested in making a change, a what-if scenario, we need to think what needs to be in the model to capture that change, to capture its effects on the outcomes we're interested in. We might be asking, okay, is data available on something? If there is, we might want to have model output that we can compare with that data. So we need a variable to capture something for the model that's comparable to this data, for example. If there's absolutely no data available at like a micro level, a level of individuals, we might question, do we want a model that's really articulated at an individual level? Is there a theory at that level about sort of how people behave or how animals behave at an individual level that we can leverage for it? Again, if we can't, we might be thinking more of an aggregate level, stocks and flows that count the number of people with certain characteristics rather than turning them into individuals. A key thing is whether heterogeneity is around. So do we need people that are very different from each other, or are we dealing with something that is very homogeneous? Let's think about a very similar to each other. Let's think about a situation where we're characterizing contamination of water, and we're dealing with a reservoir. It would make no sense to break that up into an individual level, raindrops. I mean, it makes no sense. Instead, you simulate the reservoir as a whole. There's really not a lot of heterogeneity of relevance. And sometimes stakeholders really want to see things at a certain level, like an individual level. So a common division we make here, ladies and gentlemen, that's going to be key. And for those of you pursuing projects, I've asked you to articulate your model vision in these terms. we make a distinction between factors in the model that are at a given stage of development of the model that are endogenous, that are exogenous or ignored. Now, I referenced these in my opening comments in today's lecture. And I mentioned them using casual terms and then got more specific. Let me go through them from the bottom. For ignored or excluded, I said something like things that are left out of the model. Often these are things that are consciously left out. There may be things, there are a lot often left out by fiat. You just didn't think to put it in there. But often these are consciously left out. Often we put things aside. I was talking to a student earlier today and talked about parking these things for now, not representing them for now. We'll re-examine them later as we learn from the model, as we perform sensitivity analyses, ways of testing how important they will be. Ladies and gentlemen, the next thing up, exogenous things. I want to make a distinction here between the two top items here, okay? A little bit subtle. Boy, this is highly testable. This is like plum exam testing, okay? So pay note. The two top of these are things that are represented in the model. The bottom ones are not represented. They're by definition left out, okay? Often consciously so. It's not that they don't exist. We just don't think they're relevant to the model at this juncture. We don't think they're the most important things to put in next. The two top things, ladies and gentlemen, are represented, but they're represented in different ways. Let me talk about how they're different. Exogenous factors are things we tell to the model. We pre-specify it to the model. Endogenous things are things that the model tells to us, that it generates over time. Ladies and gentlemen, that very first model, the dawning of the new semester that we created, or that we opened. Do you remember that model? Do you remember the very first day we had this model? I'll go call it up here, or call something like it up on the very first day. Can anyone tell me what were some things that were ignored by that model that might in fact be germane to the spread of infection in the real world? What things were not represented explicitly in that model? Or were not represented explicitly. Yeah.
How about the individual is
good. Excellent. Because that can have a really big impact if they get infected, for example, given some exposure. So I love it. Another thing. Yeah. Yeah, environmental conditions. To what degree, you have, for example, low air circulation, which might lead to stagnant air, me breathing in the results of microbes put in the air by someone else's cough. And that's actually a significant thing in some environments. Yeah.
just how people travel.
Yeah, okay, their traveling behavior, the sort of the degree to which they really just stay statically in one place, interacting with people to the north, south, east, and west, and northeast, etc. Versus do they actually bump around? Do they have irregular contact patterns? Excellent. There's actually a lot of things that were. Oh, okay. Thanks. I'll call up a different version. Here we go. Time to renew that, I guess. Here we go. No, get me out of here. Okay. Here we go. Boom. Give me some things that were in that model that we told to the model, that were sort of pre-specified by us in that model. Anyone?
The recovery time?
Yeah, the recovery time. Excellent. We had different scenarios which made different assumptions about that, but fundamentally, each time we were telling the model, assume this, assume that, right? What was another thing that was in there? Yeah.
Which neighbors did it?
Yeah, which neighbors did that? fact, that's a nice subtle one, because that in a way was baked in a little bit in a different way. It wasn't just a parameter assumption, it was an assumption that was specified. If you really went into it, it was specified in main in the sort of space and network area, and it said, do they have 4 neighbors or 8 neighbors? And it was baked into that assumption. We couldn't change it in a kind of nimble way for each scenario. How about something else? Yeah.
The origin of the infection?
Yeah, where it started. Okay, so that was something which was sort of given to the model. The model didn't. Okay, you could argue there it actually rolled a dice as to where it started, but it wasn't generated in some sort of ongoing basis where it was. It was pretty much a given to the model. Okay, so those are good things. These are things that the model had in it at some level. It's just that it wasn't generating these things, right? So here's any logic just in time, and we'll go and expand this, and we will go here over to the model. And what we were talking about earlier was, for example, the fact that some of these things would be specified. So like neighborhood type specified people had 8 neighbors, for example. We had each person, and each person was associated with this sort of state chart where the parameters associated with main specified the values to use for their contact rate, average illness duration, the infection probability, given exposure, etc. So there were a lot of things, in short, that were exogenous. How about endogenous things? Things that the model generated. What things was the model generating for us? What things did we not pre-specify to it, but rather it produced?
How many people get infected?
How many people get infected? Good. Great. What else?
Number of recoveries.
Number of recoveries. Yeah. That's right. So at any one time, how many people have recovered, for example? That's affected by the number of people that are infected, but also the number that, or the rate at which they're recovering. So good. How about other things? Who is infected, right? Who has recovered? Whom do they infect within the model? These are all things the model was generating. What state each given person was in, more generally, right? Those waves, those are all generated by it. Those were sort of higher level patterns. They're not really reducible to one person being in a certain state, but rather sort of the collective state amongst a set of people. Those higher level structures were associated with emergent behavior. But basically some features of the model were represented in the model itself, but in a way that it produced. So the state in which a given person was in was produced by the model. Who they infected was produced by the model. Whom they were infected by, etc. So we had a number of endogenous factors there, things that the model was generating over time. Now, why would you represent something as exogenous versus endogenous? This is actually a really key thing. And those who are going to be working on projects, they need to struggle through this a bit. Why would we represent something in the model at all? Well, so either endogenous or exogenous. Well, suppose you're interested in characterizing dynamics of a system, and you can't characterize it without this thing. Okay, you can't realistically characterize how infection spreads without talking about the fact that some people are susceptible and some people are infected. You need to capture the effect of a change, a what-if situation, or policy change, or an intervention, something you're doing to change it. And in order to capture that effect, you need to represent something. You're concerned about how it will be affected by an intervention. It would be something to represent. You want to know, how does this policy affect income distribution? You need to have income in your model. Suppose you're interested with, for example, how does the income change differ for those in urban versus rural regions? You need urban versus rural. When is it observable? And you want to compare it to some real world data to build confidence. Or when is it important for stakeholder credibility, for stakeholders to really buy into your model? Those are reasons for putting something in the model in the first place. Why would you have it be endogenous? Well, endogenous factors allow for extra flexibility in capturing effects of interventions. Sometimes we need to capture outcomes, and for those outcomes to be captured, we need certain factors that the model is producing to capture those outcomes so that it generates the outcomes we're interested in. In order to do so, we need to represent certain factors within the model. We're interested in having a model, for example, that translates to other contexts, and pre-specifying things in a fixed way may not be nearly as flexible as to have it sort of generate situations that are appropriate for the context. Endogenous factors, factors that are generated by the model, are often needed to represent certain, as we say, causal pathways, pathways that ripple through the effect of an intervention to an outcome, or that capture the evolution of the system over time. So with models, we'll often have sort of a spectrum of models, ones that just build in a lot of hard-coded assumptions about things, have very little dynamics, versus those that we call heavily endogenous. They focus on characterizing the mechanisms by which A impacts B, and B impacts C, and C impacts D, and how certain intervention impacts A, for example. These are heavily endogenous things. These are things where we have these ripple-through effects. I'm not going to go through all of these, but I have some examples, and I'll probably enable some more here. But choosing what's endogenous in your model, you'll be wanting to think through, what do I need for the model to generate to capture the outcomes I'm interested in? What do I need to represent in order to capture the effects of the interventions I'm interested in? And what do I need to have the model represent to capture behavior over time I'm interested in within the model? Okay. Without susceptible, infected, and recovered being categories in that first model, it would be hard to capture the dynamics of them. Now, you may be wondering about why this emphasis on exogenous, endogenous, ignored. I want to give an analogy here. I can't remember that I gave it the first, I don't think I gave it last time, okay? And I want to give this analogy, ladies and gentlemen. Models are like maps. Ladies and gentlemen, models are like maps. Did I talk about that in our last lecture? No. If you were new to Saskatoon, or for that matter, a long-time resident of Saskatoon, and you wanted to figure out how to bike through the city, you might use one type of map that highlights bike routes. If you wanted to drive through the city, you might use a different map that emphasizes urban thoroughfares. If you want to figure out why floods are occurring in a certain area of the city, you would use a map that showed the topography. If you're interested in why brownouts, why electrical disruptions were occurring in certain areas of the city, You would use map the electrical system. These are all different simplifications, simplified representations of the world. They capture certain features within the map, and they omit certain features. And they are useful precisely because they omit many features. If every time you had to deal with getting your routing through the city from Google Maps, you had to face navigating down to the level of blades of grass, it would offer very little benefit. Google would go out of business. Maps are useful because they hide details, that are extraneous to the problem they are seeking to serve. And you will use different maps for different purposes. The issue is not what's the true representation of the system out there. The question is what is useful for us in terms of a representation for a certain purpose. To achieve our goals, what's useful with a map. And leaving out the rest is ideal. You have only perhaps a little bit of an inkling about where the river is in that map of the electrical system. And you don't need too much detail about it in the map of the bike system, the car system. It's just a little bit of a sketch of things to orient you. So it is with models in two respects. Please note these. Number one, models, like maps, represent simplifications of the world that, of necessity, leave things out of the picture. Number two, what models leave out is specific to purpose. What's the goal for which they are used? Is it to project forward the number of cases of some illness? Is it to explain some historical pattern? Is it to ask what-if questions about an intervention? To ask about the trade-offs between this policy and this policy? Is it to identify which data points need to be collected most urgently because the outcomes are most sensitive to them? Is this model a tool for bringing people together to have a common understanding of how a system works? Is this model being used to sort of help debug our thinking about how certain processes interact? These are all legitimate uses of a model. And what we put into a model, what we leave out, will be dependent on those uses, just like what we put into a map or leave out is dependent on how we wish to use that map. What the purpose of the map is. The goal is not, in both cases, not to have a perfect map of the world. The only perfect map of the world, ladies and gentlemen, is the world itself. The only perfect representation of what's out there is that world itself. And it's not very useful to navigate within your car. You can't put it into your passengers. You can't easily call it up on your monitor. Instead, in maps and in models, we suffice with a simplified representation. What representation we have leaves out, of necessity, a lot of details. And it is useful because it leaves those details out. It runs a lot faster, it's a lot easier to build, it's a lot clearer to think through. And what details we leave out, ladies and gentlemen, will change over time as we build up the model. So the first and cardinal rule to which I will recur and to which I will come back is this idea of starting as simple as possible. You may know that a year from now you want a really, really rich model. That at the end of this semester you want to have a model with a lot of factors in it. But you start with a model with one or two factors in it and you build up. And most importantly, you learn from that model along the way. So that by the end of the semester or the end of the year, you have a savvy model with lots of factors in it, but those factors are chosen much more judiciously and in a savvy fashion compared to what would have been the case if you had chosen them up front, where it would have been naive guesses compared to what you've learned along the way. You learned along the way from new stakeholder knowledge, new stakeholder participation, unexpected model dynamics, unexpected model sensitivities, clearer thinking about it, the model points that you've been omitting things, and you end up with a much better model as a result. So if you're working on projects, you should work on them on a step-by-step basis. If you are pursuing assignments, you should pursue each step in the assignment in a step-by-step fashion, run the model, make sure it builds, run it, see the results, come to understand it before adding in lots of additional features. Proceed in logical chunks, just like you do with software development. And that is the path, a key ingredient on the path to success with models. Because modeling is a learning journey. Okay, that's all we have time for today. Next time, we are going to dive into system dynamics modeling, model mapping using causal loop diagrams, and using stocks and flows. Thank you very much.
Yeah, I got it.